As a teenager, my favorite thing in the world was dirt biking. That was my number one hobby. I think I was 12 or 13 years old when my dad kindly bought me my first motorcycle, and that continued for most of my teenage years. And my favorite thing that my friends and I would do would find jumps we could go off of. So we'd find some place, we'd ride around. I remember a dry lake bed that had a road that went through the middle of it. And so from the base of the dry lake bed, there was an embankment, and then the road leveled off and then dropped back down, and the dry lake bed continued. This was one of our favorite jumps. So let's see if I can draw a motorcycle. I don't know. Something like this. Well, as we rode toward the jump with our helmets on, not only did the center of mass of the motorcycle have a large translational velocity, but the wheels had angular velocity. The wheels are rotated in a clockwise direction. And so if you use the right hand rule for angular momentum or torque and curl the fingers of your right hand in a clockwise direction, then we can say in the plane of this page there's an x and y axis, and then the z-axis lies into or out of the page. So I believe the angular momentum sits on the negative z-axis if you follow the right-hand rule. And then we go flying through the air, and in midair, most of the time, everything went well. And we'd find ourselves up in midair. The wheels are pretty level. We'd come down and we'd land smoothly. And in midair, the wheels are still spinning. But every now and then, something would go wrong, and either the front wheel would be too low, and so when we'd land, we'd crash and go flying off our bikes with the front wheel hitting first. And then every once in a while, we'd find ourselves in midair with the back wheel too low and the front wheel up too high. And then when we landed, if the back wheel landed first, often what would happen is we go flying backwards off the bike, and the bike would get away from us. And believe it or not, I never really got hurt. I wore a helmet. I wore a big chest protector. I had heavy boots and gloves. I wore a kidney belt. There was all sorts of protective gear, and plus I was younger and had a lot more soft cartilage at the time, I guess, and so I avoided injury, but we crashed a whole lot. Eventually, over time, though, we learned we could control our motorcycles in midair. So the idea is that once you're up in midair, you're an isolated system. Now on the ground, when the wheels make contact with the earth, then any force, now and by the way, for a wheel, if there's any force of friction between the ground and the wheel, that force has an associated lever arm, so that force is torque producing, and that torque would be external to the motorcycle. In midair, there is no external torque. So that's why I say this represents an isolated system. And for an isolated system with no net external torque, then the initial angular momentum and the final angular momentum have to be equal. In other words, angular momentum is a conserved quantity. So think of what would happen if you're in midair and you increase the throttle. You pull the right hand back, and the RPMs of the back wheel increase. And so whereas you had some initial angular momentum of the back wheel, if you hit the throttle and convert the chemical potential energy in the gasoline into more rotational kinetic energy of the wheel, then the initial angular velocity increases to some larger final value, which means if there's nothing else to react, then the final angular momentum seems like it would become larger. But that can't be the case. Angular momentum has to be conserved. So what happens if you have a wheel whose angular momentum is increasing, meaning there's more and more angular momentum pointing into the page, then there has to be some part of the system that gets an increasing angular momentum back out of the page so that those changes in angular momentum are canceled out. So something must rotate in a counterclockwise direction to compensate for the increased clockwise rotation of the back tire when you hit the throttle. Well, the thing that starts to rotate counterclockwise is the whole motorcycle. So what happens is, if it's the case where the front tire is going to land too soon, so the case where we crashed, oops, I lost my whole picture, get that back again. Yeah, the case where we would land with the front tire landing way before the back tire, we just knew to avoid that happening, hit the throttle when you're in midair. That increase in the angular momentum clockwise in one part of the system would correspond to some increasing angular momentum counterclockwise the other way, so the whole motorcycle would rotate backwards and you'd level out and avoid a crash like this. So the other way, if the back tire was going to land too soon, instead of hitting the throttle, we'd tap the brake. And if tapping the brake takes away some of the clockwise rotation, then to bring everything back to a conserved value, then the whole motorcycle itself would have to rotate clockwise to restore the initial angular momentum, and the bike once again would level out. So I have a better demonstration of this. You can see, I'm sure that's not the best illustration, but there's a YouTube video that I saved. It's not one I created, but I added it to my saved videos, and I believe it's a car that's sponsored by Red Bull, and for whatever reason this jump takes place in the snow. And so I actually have two videos of this. The vehicle is moving quickly, I'm not sure how many miles per hour, gets into midair. Everything looks fine for a moment. So I have the two videos. One is a video from a camera inside of the vehicle, so you can see what it looked like for the driver. And the other video is from a just somebody watching from the stands off in the distance. And if you listen carefully in that video, you can hear the RPM, so you can hear the motor revving while the car's driving. And then it gets in midair, and I believe the driver thinks, well, I'm no longer on the ground, I don't need to use any fuel to keep me driving, so he takes his foot off the gas pedal, and you can hear the RPMs wind down. And so if there's a loss in the rotational velocity of the wheels, if it decreases, if there's a loss of clockwise rotation from the wheels, then something has to rotate clockwise to compensate for that. And so the whole vehicle ends up rotating clockwise and ends up tumbling. And looks like a pretty horrific crash, but you can see that there was enough safety measures in the vehicle that the driver actually didn't get terribly injured. So take a look at both those videos, the one where you can see the aspect of this crash from the bystander's point of view, and then watch the video where you can see it from the driver's point of view, and see whether or not you believe my story about how you can control motion by conserving angular momentum when in midair.